These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. Okay, so we can start by looking at a spring. So we might have here, the spring is at its natural length. So the natural length is where the spring would be if you never touched it and you just left it alone and it was motionless. So if the spring was motionless and alone and unstressed, it would find its natural length. Although it's also possible that you could pull the spring out to here and then release it. So let's call this the maximum expansion for the spring. So if I pulled the spring out to here and then I let go of it, what would happen?
It would go back towards its natural length.
When it gets to the natural length, would it stop there?
No, it would probably keep on going.
That's right. Now, it wants to be at the natural length, so why wouldn't it stop there? Well, its inertia would carry it past the natural length.
Okay.
So what would happen as it passes through the natural length? What would happen then?
It would start compressing the spring.
And then?
And then it would come back out.
That's right. So eventually it would get to a maximum compression. And if I was a good drawer, the maximum compression should be an equal symmetrical to the maximum expansion.
Oh.
Once it got to here, as I think you were saying, then it would start expanding. It would go through the natural length and get back to here. If there was no friction, it would get back to exactly where it started, and then the whole cycle would repeat over again. And in this introductory class, we almost always assume there's no friction. So with no friction, the spring would simply go back and forth from maximum expansion to maximum compression to maximum expansion forever without stopping. So that's one of the most important cases in the homework. So this is what's called an oscillation. And of course, there's many types of things that can oscillate, but the one that tends to be tested the most is springs, and that's one of the main things the homework focuses on. Okay. This is a particular type of oscillation. It's called simple harmonic motion, which is the main type that you're going to be studying in this class. Okay, so there's other types of simple harmonic motion, but again, the one that's focused on the most in this class is a spring. So how can we use math to describe this? So one key variable that's used here is x, and we use x to stand for the displacement from the natural length. X equals the spring's displacement from its natural length. Okay? And actually it turns out that for this part of the course, we don't really care about the displacement exactly. What we care about is the magnitude of the displacement as a positive number. So something I do in the videos is I like to just use a dot just to stand for something that's just a magnitude. So that's just a made up symbol. So what we'll focus on here is x dot, the magnitude of the displacement from the natural length. So for example, let's say that this distance here is 10 meters. And then let's say that this distance here is 15 meters. Then this distance here would be, didn't work out so well. Let's call this instead 11 meters. Let's do these numbers instead. Okay, so let's see if we understand this idea of x. What would be x when the spring is at this point? What would be the numerical value for x when the spring is at this point?
4.
Okay, good. So I was trying to trick you into saying 15, but you didn't fall for that. Good. So the key thing is x is not the length of the spring. In physics, we don't actually care about the length of the spring very much. What we care about is the displacement from the natural length. So your answer was correct. So here we could say that x is 4 meters. Okay, good. So what would x be when we're at this point?
0.
Good, not 11. Because when you're at the natural length, the displacement from the natural length is 0. So that's a very important idea. And then what would x be at this point?
4.
Because it's supposed to be symmetric, for one thing. Now, technically, I suppose here x is -4, but remember, we don't really care about that much in this chapter, so we'll just say the magnitude of x here is 4, just like you said. What we really care about is how far we are from the natural length. It doesn't matter much whether it's compressed or expanded. Okay, all right, so that's a good explanation of what x stands for. So what are the SI units for x? Meters, that's right, because it's a distance. SI units are always distance. However, that's not oftentimes the most convenient units, because a spring that was a meter long would be pretty darn long.
Yeah.
So on your problems, you might often deal with centimeters here, which means that you might have to do unit conversions to put it into SI units. All right. Let me also give you another picture here. So let's also say, look at the spring here. And let's say that this distance is 9 meters. So what would x be at this point?
2.
The magnitude of x would be 2 meters. Good. So normally on problems, the only points we usually care about are maximum expansion, natural length, and maximum compression. But it's possible that you might also focus on an intermediate point, like this. Okay, so that's what the meaning of x is. Now another concept that's important for oscillations is amplitude. So what would you say is the amplitude of this oscillation?
4?
That's the right answer. So what does amplitude mean? So the amplitude is the maximum x. Amplitude is the maximum x, which means it's the maximum displacement from the natural length. We don't need a special symbol for that. We'll just call it amplitude is the maximum value of x, the maximum displacement. And amplitude is an important concept for lots of examples with oscillations and waves. So now if you think about it, there's a weird or subtle difference between x then and amplitude. Would you agree that, so if I take the spring over here and then I let go of it, would you agree that x will be continually changing?
Yes.
Because the spring will move from here where x is 4, x is 3, x is 2, x is 1, x is 0, x is 1, x is 2, x is 3, x is 4, and then back again. X will be constantly changing.
Yeah.
But will you agree that that doesn't mean the amplitude is changing?
Right.
The amplitude, so even when you're not at the maximum displacement, the amplitude still refers to the maximum displacement. So just to make sure that's clear, what would x be at this point?
4.
And what's the amplitude?
4.
What would x be at this point?
2.
And what's the amplitude?
4.
Still 4.
Okay.
The amplitude doesn't change just because the spring is moving. Just because you're not at the maximum displacement doesn't mean we can't talk about what the x would be if you were at the maximum displacement. All right, so there's a subtle difference between these two concepts. Okay, what's the SI units for amplitude?
Meters?
Because that is a distance. Okay, good. All right, so that's our second concept. We're doing this in the context of a spring, but amplitude refers to lots of other oscillations too. So by the way, is from here to here equal to the amplitude?
Half the amplitude. No? It's full amplitude?
So you're right, it's not the amplitude.
Okay.
It's twice the amplitude.
Twice the amplitude.
Not half the
Oh, yeah,
amplitude,
sorry,
right?
sorry.
Okay.
The amplitude would be half of that.
That's right.
Yeah.
Okay. The key thing is that's a common mistake people make. So oftentimes when people try to find the amplitude, they think it's from here to here. But it's not. It's from here to here. Or from here to here. Okay? Okay, so what's the next concept that we need? The next concept that we can use here is the spring constant. Do you know what the symbol is that your course uses for spring constant?
K?
Lowercase k.
Yeah.
That's correct. K for constant. Okay, I think it's always important to know the SI units for every concept. This one's not so obvious, you may not know this. Do you know what the SI units are for K?
Is it Newton meters, or?
You might be thinking of the right thing. If you're thinking of newtons per meter, then you're
Newtons
right.
per meter, yeah.
So it's not newtons times meters, but it's newtons per meter.
Per meter, okay.
So let's say that this spring has a K of 3 newtons per meter. What does that mean? How would you describe in words what that tells us about the spring?
You need 3 newtons of force to compress it or stretch it 1 meter.
That's a good explanation. Yes, that's very good. Here we have a fractional unit. So a good technique to use when you have a fractional unit is to put a number on the bottom. And what would be a good number to put on the bottom?
1.
And that's actually what you did. In your explanation, you used the number 1. So that's a good technique for a fractional unit. This means that if we compress it 1 meter, to do that, to compress 1 meter would take a force of 3 newtons, or the spring would fight us with a force of 3 newtons.
Okay.
Does that mean we're actually compressing it by 1 meter?
No.
It's just hypothetical. How much force would it take to compress it 2 meters?
6.
6 newtons. And how much force would it take to compress it 3 meters?
9.
9 newtons. So that gives us a feel for what the K tells us.
Yeah.
So let's say that we have a K that is 100 newtons per meter. So here's spring 1, here's spring 2. What does it mean when K is very big? Does that mean that the spring is very stiff or very loose?
Stiff.
Yeah, so K is a measure of how stiff the spring is. The larger the K is, the stiffer it is, the harder it is to stretch it or compress it. Okay, good. Okay, so now we have 3 concepts for spring oscillations that can be useful to us here. So then the next concept that's useful to talk about is period. Do you know what the symbol is that your course uses for period?
I think it's T.
Capital or lowercase?
Capital.
Capital T. Good. Do you know what the SI units are for period?
Second? I don't know. Seconds maybe? Meters per, or just seconds?
Take a guess.
Just seconds.
That are correct units. That's
Okay.
good. Those are correct units. How can you remember that? Well, capital T should remind you of time. This is a type of time, so it makes sense that it's measured in seconds.
Okay.
Now, these are correct units. There's another correct units, though, that I think are more useful for a beginner. The more useful correct units are seconds per cycle. So both of these are correct, but I think this gives us a better sense of what period means. So for example, suppose that I told you that the period for this spring's oscillations was 3 seconds per cycle. How would you interpret that in words?
It takes 3 seconds for it to, so if you had stretched it, it would take 3 seconds to go to the natural length, compress the natural length, and come back.
Okay, that's good. That's a good explanation. We can simplify that by using the technique we talked about. What number can we put down here?
1.
So what you were basically saying is it would take 3 seconds to go through 1 cycle.
Yeah.
So what you said was correct. 3 seconds to go through 1 cycle of expansion and compression. That's right. So as you said, if you started here, it would take 3 seconds to get back to here. Or if you started here, it would take 3 seconds to get back to here. Okay? So notice, you can see why we're using a T for this, because it's a type of time.
Okay.
So how would you describe the period in words then? What's the definition of the period?
3 seconds to complete 1 cycle.
But what's the definition of the concept? For example, x is displacement from natural length. What's the definition of period?
Time to complete a cycle.
That's right, time to complete 1 cycle.
Okay.
It's just important to know the definition.
Yeah.
So the point is, remember that we interpret it by putting a 1 on the bottom. So it's the time to complete 1 cycle. Okay. The period tells us how long it's going to take to complete 1 cycle. Now, let's say that I start here and I move here. What fraction of a cycle is that? If we start here and move here, what fraction of a cycle is that?
Quarter.
That's a good answer. Good. Most people answer wrong. Most people say 1/2, because it's half the distance on the board. But you got that correct.
Yeah.
Okay, that's important for solving problems. From here to here is only 1/4 of a cycle. That's right. Because from here to here is what fraction of a cycle? It's only half of a cycle. A whole cycle would be going here and then going back again. Okay, so that turns out to be important to remember that half the distance on the board is actually a quarter cycle. And a full distance on the board is really only half a cycle, because we have to go in both directions. Good? Okay. So here's the period for this spring, and my question is, how long would it take the spring to go from A to B?
3 seconds.
Because that's 1/4 of a cycle. If one cycle is 12 seconds, then a quarter of a cycle is 3 seconds.
Okay.
That's right. You can even do this as a unit conversion. It's 12 seconds per cycle, and this is how much of a cycle?
Quarter.
So as a unit conversion, this would be times 1/4 cycle. Well, 12, and then the cycles would cancel, and we'd have 12 times a quarter is 3 seconds. Okay, good. All right. That might not seem so exciting, but students often get that wrong because they think this is half a cycle.
Right.
So that's so the point is, this is not always the answer. It's only the answer if you're dealing with one cycle, but you can still use it to get the answer. Okay. So how long would it take to go from here to here?
6 seconds.
6 seconds, because that's half a cycle. How long would it take to go from here and then back to here?
12.
12 seconds. Yeah. How long would it take to do 4 cycles?
48?
48 seconds.
Yeah,
Okay,
good.
good. Okay, so now we can see how we can use period to answer questions. The key to using the period is asking how many cycles is the spring going through, or what fraction of a cycle is it going through. Okay, if you're told the period, there's another concept you can figure out from that. I don't know if you picked up on this from class. Do you know what's another concept that you can figure out from the period that we haven't talked about yet?
Frequency?
That's the right answer.
Yeah.
Frequency. Good. So that's a key concept in this chapter. So let's do the same thing for frequency that we did for period. What would be a good symbol for frequency?
F.
That's right. And what are the SI units for frequency?
Seconds?
Say that again?
Seconds?
Okay, those actually turn out not to be right. If it was, it would be the same units as period, but then there wouldn't be much difference between them.
Yeah.
So first of all, there's a name for this unit. There's a special name for this unit, which is hertz.
Oh, okay. Yeah, that's right.
That's worth memorizing. I think it's good for students to memorize the key units. When you take your exams, are you allowed to bring notes with you, a cheat sheet?
No, but she gives us a formula sheet.
Okay.
But
Okay. Now that formula sheet probably doesn't include units, so
No.
the units are things we should memorize. It's good to memorize the units. Okay, now there's a formula that relates period and frequency. Do you happen to know what that formula is?
yeah, or 1/T is frequency? Or something like that.
That's good.
Okay.
Well then, if we know that formula, we should be able to figure out some units for frequency.
So it's just inverse or 1/S?
That's right. So at first you were guessing that this would be seconds,
Yeah.
but actually it turns out to be 1/seconds, which might sound similar, but they're quite different things. Okay? So here's 2 correct units for frequency. You could say it's hertz, or you could say it's inverse seconds.
Okay.
However, neither of these I think is most useful for a beginner. Remember, these are the most useful units for period, so how would we translate those into units for frequency?
Cycles per second?
Because we're just doing the reciprocal. So there's 3 different correct units for frequency, but for a beginner I think this is the most useful way to think about it. So for example, if I tell you that the frequency of this spring is 4 hertz, how would you translate that? How would you, what does that mean?
Okay.
What does that mean in words?
There are 4 cycles completed in 1 second.
Good. So the first thing you might have done there was remember that hertz are really cycles per second. And then since that's a fractional unit, you put this number 1 here, and you said in 1 second it's going to complete 4 cycles. So notice it must be moving quite quickly,
Yeah.
right? Faster than I can move my hand. It's going back and forth 4 times in 1 second. All right. Okay, so that's the meaning of the frequency. Good. So going back to here, do you remember, what did we say was the definition of period? What was the verbal definition for period?
How long it takes to complete a cycle?
How long it takes to complete one cycle, that's right. How much time it takes to complete one cycle. So what would be the verbal definition of frequency?
How many cycles how many cycles are completed per second?
Good, that's right. Now, I think people have better understanding if instead of saying per, they say in one. So we could say this is how many cycles are completed in 1 second. Well, so what you said was correct, but maybe this is a little bit clearer. So what's the definition of the frequency?
How many cycles completed in 1 second?
And what's the definition of the period?
How many seconds it takes to complete a cycle.
Excellent. So one thing I notice is that people tend to confuse these two things with each other. A lot of the time when the problem asks for frequency, they're accidentally thinking of the period, or vice versa. And you can see how they get confused because they are similar, but they're also different. The best way to see how they're different is to use these units to see how they're different from each other. Okay, good. Well then, moving on, we said that if you know the period, you could use this formula to find the frequency, or vice versa. Do you happen to know what's another concept that we could figure out from frequency?
I don't know.
So the next concept is what's called angular frequency. Does that sound familiar to you?
Yeah.
Do you know what the symbol is for that? Can you draw the symbol for that?
Is it like a W?
There you go, it's like a W. That's right. It's actually the Greek letter omega.
Okay.
Okay, so that's our symbol for angular frequency. All right? So now we need to understand what this concept means. So how are we going to understand what that means? So the first thing you have to understand is that the physicists here use a trick. Notice here that we're studying cycles. But the physicists said, well, I think a good trick would be to pretend that a cycle is a circle. So we're going to use a kind of a weird trick. We're going to pretend that when we've gone through a cycle, it's as if we've gone through a circle. We're not. So the spring is not actually going through circular motion, but it turns out to be convenient to pretend that a cycle is like going through a circle. So one thing we're going to do here is we're going to say one cycle is going to be treated as a circle. Now, let's review something about circles. How many radians are there in a circle?
2 pi?
That's right, 2 pi radians in a circle. So, how many radians would there be in a cycle?
2 pi.
Because we're pretending that a cycle is a circle. So, this is going to be the key idea for this concept. We're going to pretend that one cycle is like 2 pi radians. Now, it's only pretend because the spring is not actually going through any radians. But, so for example, if we go from here to here and back to here, we'll pretend we went through 2 pi radians, even though we didn't.
Okay.
And if we go from here to here, how many radians did we go through?
Pi.
Pi radians, half a cycle. So if we go from here to here, how many radians did we go through?
1/2 pi.
Yeah, pi over 2.
Pi over,
that's
yeah,
right.
yeah, that's
if we go through 2 cycles, how many radians is that?
4 pi.
Okay, good. So what are the units for angular frequency? Well, by analogy with regular frequency, the units here, if this was cycles per second, these units are radians per second.
Okay.
At least those are the most useful units. Confusingly, there's also other units you could use. It's also correct to just say they're per seconds. So confusingly, these units could be correct for frequency or for angular frequency. However, it's certainly easier to understand if we use these units. So we'll stick with these units of radians per second. So suppose I tell you that this spring has an omega of 6 pi radians per second. What does that mean?
It covers 6 pi radians in a second.
That's a good start. So instead of saying A, we can say 1. We can be more specific that way.
Okay.
That's a good start, but what the heck are 6 pi radians? What is it?
Can I assume that's a cycle or not?
Well, is it? How many cycles is this?
Oh, 3.
So how many cycles is it doing per second?
Oh, 3 cycles.
So this is just a fancy way of saying 3 cycles per second.
Oh.
Why are we using this weird notation? Well, it turns out that some equations turn out to be simpler using this concept. Right now, it's just kind of a pain because it seems like a weird way to think about this. But it turns out that as you develop this, this part of physics, this turns out to be a useful concept. But for now, it's just a little bit of a pain to figure out what it means. But the key thing is it's not as hard as it seems. It's just a fancy way here of saying 3 cycles per second.
Okay.
This is just a fancy way of saying 3 cycles per second. So for example, what would it mean if the spring had an angular frequency of 8 pi radians per second?
4 cycles in 1 second.
4 cycles in 1 second. That's right. What would this mean?
Half of a cycle in a second.
Yeah, half a cycle. So if you wait 1 second, it'll go from here to here.
Okay.
Okay, so this is not as mysterious a concept as it seems. It's just a fancy way of telling you the real frequency in kind of like code. Now, if you think about it, then let's go back to an easier case. So what does this mean?
3 cycles in 1 second.
It tells you that F is 3 cycles per second. So would you agree that we just kind of proved this formula?
Yeah.
Because 6 pi is 2 pi times 3. So notice what we're trying to do in this flowchart is show the formula that links up all the concepts. So this is a formula that technically you could figure out if you forgot it by using these little examples. Hopefully it'll just be given to you on the test on that formula sheet that you're going to be given. So here's the relationship between omega and F. So if you know F, how do you figure out omega?
Multiply it by 2 pi.
And if you know omega, how do you find F?
Divide it by 2.
That's right, that might seem obvious, but I noticed that if people try to cut corners and they don't write the equation down, they often reverse things.
Okay.
For example, I often reverse things. Oftentimes, if I know F, I divide by 2 pi to find omega, which is really wrong. Basically, I guess people often misremember the equation. So remember, this is not the equation.
Okay.
This is the correct way to do it. So the safest thing is to always write it out. Okay. So now we understand how here we're using this trick of treating 2 pi radians as 1 cycle. All right, good. How can you figure out what the angular frequency is from information about the spring? So it turns out that this concept links up with our friend the spring constant. What's the symbol for the spring constant?
K.
Little k. What's the SI units?
Newtons per meter.
That's right. So it turns out that if you know the spring constant, you can figure out omega. Okay, good. What does this symbol stand for?
Angular frequency.
And this?
Spring constant.
And this?
Meters.
Now, it can't be a unit because then it
yeah,
would match up. What is little m? What concept does little m usually stand for?
Mass.
So it does stand for mass. Here.
Okay.
That's right. It shouldn't surprise you that the mass affects the frequency. This is just saying that the more massive the spring, the less frequently it can oscillate. And this is also telling us that the tighter the spring, the faster it's going to oscillate. So this equation actually makes some sense. It's saying a tight spring would have a big K, which would make it sense that it's going to whip back and forth very quickly.
Okay.
On the other hand, if it was attached to something very massive, that would slow it down and decrease the frequency. So it makes sense that M is on the bottom and K is on the top. Okay? So hopefully that's another formula that will be on that formula sheet that you're given. You have to use SI units in this formula, otherwise it won't come out correctly. This will probably be given to you in SI units. What are the SI units for mass?
Kilograms?
That's right. But it might be natural to be given the mass in grams.
Right.
Well, then you'd have to do a conversion before you could use this.
Okay.
All right, good. Let's see. something that's interesting here is notice the frequency has nothing to do with the amplitude. So if you pull the spring a long way out and let go, its frequency will be just the same as if you only pull it a short way out and let go.
You say that again?
So I could take a spring, pull it a long way out, and then let go. And then it would end up moving very quickly, right?
Okay.
On the other hand, let's say I take the spring and I only move it a short way out and let go. So it goes back and forth like this. It turns out that in both cases it will have the same frequency.
Oh, okay.
It's true that the spring that you pulled out further will be moving faster, but it also has a greater distance to travel. And those two things are going to exactly cancel each other out.
Okay.
If you only stretch the spring out a small distance and let it go, it's not going to move very fast. But it also doesn't. It's not going to move very fast, but it also has a shorter distance to go, and those two things cancel. So this is. It turns out that the amplitude doesn't go into this flow chart. Only the tightness of the spring matters. Here's what I wanted to mention. So what does the M stand for?
Mass.
Mass. Whose mass? So yeah, whose mass?
The whatever is attached to the spring.
That's a good answer. That's a good answer. So what you didn't say was the mass of the spring. So on these problems, we generally assume the spring has no mass. We assume the spring has no mass. M is the mass that's attached to the spring. Good. Okay.
And then mass. And so just figure anything particular, or just
Figure out anything that we're able to figure out at this point.
so.
Are you allowed to use a calculator on your tests?
Yeah.
All right, so go ahead and feel free to use your calculator on these problems too, if you need it.
Oops. that's everything.
Okay. All right. So let's see. So one thing you did at the start here is you took the numbers and you put down symbols for them. So for example, you said that this was actually the frequency. So that's good. Notice I didn't tell you this was the frequency. How did you know that number stood for the frequency?
Oh, just because of the units.
That's right. So that's one reason why it's important to know the units, because otherwise we can't identify the concepts. Okay, so you did that correctly. So how would you interpret this frequency in words? What does it tell us?
It takes 4 cycles are completed in 1 second.
That's right. 4 cycles can be completed in 1 second. Then you use this equation to find the period. How would you interpret this number?
It takes 0.25 seconds to complete 1 cycle.
That's right. So you could have said the units were seconds per cycle, although these units are correct too. Okay, good. Then something that was a little bit interesting happened. The next thing you tried to do was to figure out omega. Or actually, no, the next thing you tried to do was to use this equation, but then you realized you'd actually skipped an equation, and that's the kind of the point of the flowchart. The point of the flowchart is it tells us what order we usually have to use these equations in.
Okay.
So, for example, I gave you the frequency, so before we can jump all the way over to this equation, as you figured out for yourself, we have to use this one. So the flowchart just tells us the order that we usually use the equations, and you figure that out for yourself. All right, so you found omega correctly. You used this equation, you correctly got rid of the square root. Okay, excellent. Okay, so those are all some good techniques. Notice one thing you can't figure out here is the amplitude of the spring.
Right.
Because that's actually unrelated to all this information. Okay, good. By the way, we're using here the spring as a specific example, but many of these ideas apply to other types of oscillations and to waves as well. Okay? Let's go back to this picture.
Would that be max expansion on the top?
Thanks, my mistake. Okay, one variable that we said we could use to describe this is x. So what could we say about x at this point?
X equals 0.
Good. What can we say about x here?
X equals A.
X is the amplitude. You could say that. That's right. Something else you could say is that this is the point with the maximum x.
Okay.
And what could we say at this point?
Also the maximum X?
It's also the maximum if we focus on the magnitude. You could also say that x here is also equal to the amplitude. The magnitude of x is also the amplitude at this point. Okay. So there's other points where x is between 0 and the maximum, but we don't often need to focus on those for solving problems. These are the 3 points that we're normally going to focus on. So what's another variable we can use to describe the spring? Another variable would be the speed that it's moving at. What would be a good symbol for the speed that the spring is moving with?
Velocity?
Yeah, so what would be our v? That's right. And what are the SI units for that?
Meters per second?
That's right. So that's another variable we haven't talked about yet. Now, would you agree that the velocity will be constantly changing?
Yeah.
Yeah. For example, as the spring is moving, if I let go of the spring here, the spring is going to, it's going to pull on itself and speed itself up more and more and more and more and more. But then once it gets to this point, the spring is going to start trying to push back and slow itself down because it doesn't want to compress anymore. So the speed will be constantly changing. All right. What can you say about the speed at this point?
It's 0?
That's right. That's right. How do you know? How do you know the speed is 0 here?
Because that's like right, if it's at its max expansion, it's about to be on its way back. So, I don't know. So it's not moving anymore. It can't go any further.
Good. We haven't quite put our finger on why exactly that means v is 0. You're on the right track. The key thing is, this is the point when it's changing direction.
Okay.
And what's your speed at the instant that you change direction?
0.
0. Okay, so the key thing is, this is the point when we're changing direction, therefore the speed is 0 there. That's an idea that's often useful in kinematics as well. The point where you're changing direction is when your speed is 0. Okay, good. That's right. So what can you say about v over here?
It's also 0.
That's right. All right, so now let's introduce another concept. Actually I should have given myself more room for that. So stepping back for a second, one thing that's important to realize in physics is that what you're mainly learning in physics is a bunch of frameworks for solving problems.
Okay.
We're learning a bunch of different frameworks for solving problems. For example, what was the very first framework that you covered in this class? The first framework was kinematics. Projectile motion is a type of kinematics. What do you think was the second framework you covered in the class?
Oh gosh. Would that be after projectile motion? We did Newton's laws. Is that still
That's what I was going for.
Okay.
Which one in particular? The one that you used as your framework was Newton's second law.
Yeah.
So the main next key idea was Newton's second law. What's the first fundamental equation that you write down when you're going to solve a problem using Newton's second law?
F equals ma.
It's on the right track, but let's fix that a little bit. First of all, it's got to be the sum of the f.
Yeah. Okay.
Equals ma, and it's got to be specified for a particular component. So we'd say sum of the fx equals max, and sum of the fy equals may. These are the first equations you should write down when you're using this framework for solving a problem. So, good. Any idea what the third framework is in the course?
Rotation, or is that's still the same stuff?
Rotation can still be analyzed with Newton's second law,
Yeah.
because there's a rotational version of Newton's second law.
Okay.
So,
now.
what else? So the next one was actually conservation of mechanical energy.
Oh, yeah, okay.
Conservation of mechanical energy. Now again, what's the key equation you write down first when you're doing a problem about conservation of mechanical energy? I think the best equation to write down is a very simple one. Just this very simple equation here. But do you know what the capital E stands for? Capital E here doesn't just stand for energy, it stands for total mechanical energy. So in this formula, capital E stands for total mechanical energy. And there's only one other framework that you've covered so far in the course. The last framework is conservation of momentum. And I wrote down the key equation to write down first when you're dealing with conservation of momentum. The sum of the initial momentums equals the sum of the final momentums. Okay, so when you're doing a problem on the exam, one of the first things you should ask yourself is, what's the right framework for solving this problem? If you don't know how to solve it, just run through each framework in your head until you come across something that might work.
Okay.
All right? Well, here we're dealing with oscillations in a horizontal spring. Take a guess, which of these frameworks might be most useful for oscillations in a horizontal spring?
Conservation of mechanical energy?
That's right, yes, that's the one that we're mainly going to be applying here.
Okay.
So let's focus on this. Do you remember what the capital E stood for?
Total mechanical energy?
That's right.
Okay.
So what are the types of mechanical energy? What's one type of mechanical energy?
Kinetic?
That's right. What's the symbol for kinetic energy?
K?
Capital K.
Yeah.
Good. What's the SI unit for mechanical energy? For kinetic energy?
Um,
That's an important one to review.
Yeah.
The units for energy are joules.
Joules, oh gosh, yeah.
And do you happen to know what the formula is for kinetic energy?
1/2 mv squared.
That's right. What does the M stand for?
Mass.
And the V?
Velocity.
And you have to use SI units in this formula. So for example, in this context, this would be the mass that's attached to the spring. And this would be the velocity that the spring is moving at, since we're going to apply it to these types of problems. So notice again, if you were given the mass in grams, you'd have to change it into kilograms before you could use that formula. So kinetic energy is energy you have because you're moving. So when you're moving faster, what happens to the kinetic energy?
Goes up.
Yeah, higher the V, the bigger the K. It's energy you have from moving. It's always important to know when things are zero. So when would the kinetic energy be zero?
When you're not moving.
Yeah, when you're if you're not moving,
Or you're not
just when V is zero.
Yeah.
If
so
V is
constant
zero.
velocity?
Pardon?
No.
We'll talk about that more in a second.
Okay.
When V is zero, kinetic energy is zero. Okay, we'll come back to that in a moment. And when would K be maximized? When V is maximized.
Okay.
Okay, good. Okay, what's another type of mechanical energy?
Potential?
Yes.
So
No.
gravitation.
So there's gravitational potential energy.
Yeah.
That's right, there's gravitational potential energy. What's the symbol for potential energy?
It's switching between like PE and U.
Yeah, that's right. I think, so that's right, it could be either. I'll use capital U.
Yeah.
Okay, but let's actually call that this, GRU, for gravitational potential energy. Do you know what the formula is for that?
MGH.
That's correct. Do you know what the SI units are for gravitational potential energy? Because it's a type of energy. Something I should have mentioned is gravitational potential energy a vector or a scalar?
Vector.
Actually, it turns out that energy is a scalar.
Oh, okay.
What difference does that make? Does energy have to be broken into components?
No.
No. You could have used that to figure out that it's a scalar, not a vector.
Okay.
Force. Notice how when I wrote this equation, I put in little x's and y's, because force is a vector. But here I didn't put any x's and y's, because energy is a scalar.
Okay.
Do we need to choose axes in a positive direction for energy? No, because it's a scalar, not a vector. So that's why it's important to know that this is a scalar. It tells us that we don't break it into components, and we don't need axes in positive directions. Is kinetic energy a vector or a scalar?
Scalar.
Because all types of energy are scalars. So again, this doesn't get broken into components. What does the M stand for?
Mass.
And the G?
Gravity. Force
What
of
about gravity? It's actually not the force of gravity. This is the acceleration due to gravity.
Okay.
9.8 meters per second squared. The force of gravity would be your weight.
Right.
G is the acceleration due to gravity, and H is
Your height.
the height. You can choose whatever you want to be a height of 0. So this would be the height above the 0 point. Okay? So if you're at a height of 0, your gravitational energy would be 0. All right, any other types of mechanical energy that you've seen in the class?
Elastic potential.
Yeah, elastic potential energy, which is, another name for that would be spring potential energy. But elastic energy is kind of more general name, that's right. So we could call that the elastic or spring potential energy. What would be a good symbol for that?
ELU.
Good. I'll call it SPU because we're mainly going to be focusing on springs.
Okay.
For example, in the homework, the only type of oscillation they did, every single problem was about springs.
Yeah.
But you're right, you could, if necessary, you could generalize this to other elastic things. Okay, so we can call this SPU. Happen to know what the formula is for that?
1/2 kx squared.
That's good, that's right. It looks kind of like the formula for kinetic energy. What's the K stand for?
Spring constant.
And the X?
Displacement.
From the natural length.
Yeah.
Yes. And what's the SI units for X?
Meters.
So if x was given in centimeters, you'd have to do a conversion before you could plug it into this formula. What's the SI units for the spring energy?
Joules.
And is it a vector or a scalar?
Scalar.
So it doesn't get broken into components. Okay, good. Okay, going back to talk about this object here, would you agree that gravitational energy is not very interesting for a horizontal spring?
Mm-hmm.
But why? Why is the gravitational energy not interesting for a horizontal spring? Well, the key is, here's a trick question, what's the difference between the gravitational energy here and the gravitational energy here?
They're the same.
Because they're at the same height.
Yeah.
They're the same because they're at the same height.
Yeah.
That's right. Well, so that's why it's not interesting. For a horizontal spring, the gravitational energy never changes. So it's not going to turn out to be very important to us. Okay? And of course, you could even say that this was zero height, and then it would even be zero at both points. So instead, we're going to focus on kinetic energy and the elastic spring energy. When would this be zero?
It would be zero. At the natural point?
Yeah, when you're at your natural length. That's right. Wouldn't you agree that when the spring is at its natural length, it doesn't have any energy stored in it?
No. It wouldn't have...
When it's at its natural length,
it hasn't been stretched or compressed.
Yeah,
Okay,
that's when it's happy and it doesn't have any energy in it.
Yes.
On the other hand, when would this be maximized?
At the mass expansion or max compression.
That's where the spring is very unhappy and there's a lot of energy stored up in it.
Yeah.
Just like a bow that's been pulled back.
Mm-hmm.
Okay, good. Now remember we said that the idea we're going to use here is conservation of mechanical energy. So as the spring moves, the kinetic energy can change and the spring energy can change. But the sum is going to stay constant. The sum of all the energy is going to stay the same. Okay, so let's see, going to here, what can we say about the spring energy at this point? What can we say about the spring energy?
It hasn't been
At this
stretched
point.
or compressed.
Well, at this point in the picture.
But like if it had been moving, then wouldn't it have kinetic energy?
That's true. But remember what I was asking you a second ago is what can you say about the spring energy?
Oh, spring energy.
I mean,
Sorry,
I should have been
sorry.
more specific and said the spring's potential energy.
Potential. Oh, yeah. Sorry. Yeah, zero.
Good. Here's where the spring's energy is zero because x is zero. So what can you tell me about the kinetic energy at this point?
At what point?
At the natural length.
It hasn't been stretched or compressed.
Well, no, so remember that what we're thinking of is we pulled it to here,
Oh, okay.
and then we let go. So it's moving back and forth like this.
So isn't it at its?
So when it's at this point, what can you say about the kinetic energy?
It's. I don't know.
Let's talk about that a little. Now we said the spring energy was zero.
Yeah.
So where did all the energy go?
So it has to be equal to the spring energy at its max.
That's right, that's right.
Yeah.
That's right. I was going for something a little bit simpler than that, but that's right. So if the spring energy is zero, where did all the energy go?
All into kinetic.
Into kinetic energy. So all I was going for is this is the point where kinetic energy must be maximized.
Oh, okay.
That's not really all that obvious. Many people wouldn't see that. But the point is the spring will be going fastest as it passes through the natural length. The spring will be going fastest because that's the point where none of the energy is in potential energy, so it must all have been put into kinetic energy. Okay, so this is where the spring is going fastest. So, this is where they have the highest kinetic energy. So what can you tell me about V at this point?
It's at its max.
That's right.
Okay.
So now we've completely described the key things to know about the natural length. The natural length is when there's no potential energy and it's all kinetic energy.
Okay.
So let's go back up here when you're ready to the maximum expansion. So at maximum expansion, what can we say about the spring energy?
It's at its max.
Because x is at the max.
Yeah.
And what can we say about the kinetic energy?
It's zero.
How do you know?
Because velocity is zero.
That's one way, yeah. We know we're changing direction here, so speed is zero, so kinetic energy is zero. But you also know it because of conservation of energy. If all the energy has been put into spring energy, what's left for the kinetic?
Right.
Zero.
Nothing, yeah.
Okay, so there's two ways to see that.
Okay.
All right, so then let's do a similar description of this point at maximum compression.
So it's at its maximum potential energy, and its kinetic has to be 0.
Again, X isn't maximized, so all the energy is in spring energy and nothing is left for kinetic energy. We're changing direction, so V is 0. So when you're solving problems about conservation of energy, it's important to know when things are 0. So this is a table here that helps us to summarize when things are going to be 0 when we're solving problems, and also helps us to summarize when things are going to be maximized. Okay? So we can label this as problem 2. Okay, let's try this. Done?
Okay. Yeah.
Let's see, so you had a good start here, you were writing down the symbol for each concept, and you also wrote down the single symbol for the question. That's good. And what framework did you use? Conservation of mechanical energy. That's good. You wrote down your framework equation here, so that's a good step as well. So it looks like you were assuming here that the initial potential energy, no, you said you assumed that the initial kinetic energy was 0. How did you know the initial kinetic energy was 0?
Because when it was, by the time it got compressed, it wasn't moving. We compressed it to a point that it wasn't moving.
So it was at maximum compression.
Yeah.
Basically the point is, it was released from maximum compression, so it hadn't had any time yet to pull up any speed at that point. Good. And the question asked you for the point of maximum speed, but you figured out that that meant the speed at the natural length. Notice the problem didn't say to focus on the natural length, but from the work we did before, we know that the maximum speed occurs when it's at the natural length. So you said the final point was at the natural length. So something that might have been a good thing to do is to say that you're labeling this as your initial point and this at the natural length as your final point.
Sure.
Okay, good. So at the final point, what's the spring energy? 0. So that simplified the final energy. Okay, and then you simply set this energy equal to this energy here, and you worked out an answer. Okay, that looks like a good technique for the problem. So let me add on to that part B. Let's also try part B.
No. Can I use the, okay, here with the acceleration. Can I use the kinematic equations?
What do you think?
Yes. I don't have them memorized, but
So how do you know when you can and when you can't use the kinematics equations?
I don't know.
So the key thing is, kinematics equations apply when we have constant acceleration.
Okay, and we would here, wouldn't we?
And when do you have constant acceleration? You have constant acceleration when you have a constant force, right?
Yeah.
So is the spring force here going to be constant?
I guess not.
Right. We haven't talked about that too much. I think we talked about it a little bit. For example, when you're at the natural length, there is no spring force, because the spring is happy. Something that you covered earlier in the course that we haven't been discussing here is the equation for the spring force. Do you remember this equation from earlier in the course?
Mm-hmm.
All right. So doesn't this show the spring force is not constant? Because
Right.
whenever you change your position, that changes the force.
Uh-huh.
But then Newton's second law tells us if the force isn't constant, the acceleration isn't constant. But the kinematics that you studied is constant acceleration kinematics.
Okay.
So if the acceleration is not constant, you can't use kinematics. That's a good thing for us to discuss. So the reason that we've been focusing on conservation of energy and not Newton's second law is, Newton's second law is oftentimes not very useful for an oscillating spring because it would be too complicated because the force is constantly changing.
Okay.
And then kinematics is not useful because the acceleration is constantly changing.
Okay.
Can you think of any other approaches to solve a problem?
Yeah, actually. Oh.
What did you plug in for M?
3? Oh, 4. Oops.
I think you got that confused with X.
So.
Okay.
Yeah, that's all I got.
Okay, so let's talk about this. So going back to part A, you started by writing this equation here. You did this correctly. As the problems get harder, I find that it's convenient, or we make fewer mistakes if next we could write the full equation like this. And then you said that the initial kinetic energy was 0, and the final point is at the natural length. So then you could plug in spring energy 45, and our kinetic energy would be 1/2 m the final squared. So that takes you to the equation that you were already using over here.
Mm-hmm.
So this is basically the same thing you did, but this is an organized way to attack that.
Yeah,
That it's
definitely.
flexible as we go on to harder problems. Okay, but you didn't have any trouble with this first part of the question. The second part gave us a little trouble, so that would be a good part to highlight, because that's
Yeah.
something you might see on the test.
Definitely.
Okay, so as we were reviewing here, For horizontal spring oscillations, Newton's second law and kinematics are not too helpful because the force is constantly changing and the acceleration is constantly changing. But here's where it's helpful to have gone over this flowchart that we talked about earlier. The tricky thing here is that I didn't give you any clues that you had to shift over to this, but eventually we worked that out. So the point is, I think if I'd asked you how long would it take to go through one cycle, you would have thought of this.
Yeah.
But by asking how long does it take to reach the maximum speed, what you had to say is, well, the time to reach the maximum speed is really the time to reach the natural length.
Right.
And the time to reach the natural length is really the time for 1/4 cycle. That was the key.
Yeah,
so that was, the question was really asking you how long does it take to do a 1/4 cycle, and that's the type of problem that we were practicing earlier.
Okay.
And that's how you, and when you were thinking of it that way, that's how you knew that what you needed was the period. Okay, good. And once you thought of that, it looks like you used a good approach. You went all the way from the right-hand side of the flowchart to the left-hand side, and you got what you needed. And you notice this is not capital T, it's a lowercase t. Good, because it's not the actual period. Okay, good. So this will be problem 3. Okay, so I'll give you a hint. This problem is a little bit more complicated than the ones we were doing before. We're going to need also another framework. So remember, here's the 4 frameworks you've covered so far in the course. So besides conservation of mechanical energy, we might also need another framework that you also hopefully have studied. So give this a shot, and if you get stuck, I'll give you some help. Okay. So I think a good way to think about this problem is to identify what are the key points in time that we care about. There's really 3 key points in time that we care about. So t0, the first point you care about is the instant before the collision. Then the next point you care about is a millisecond later, the instant after the collision. And the next point you care about is the point of maximum compression, because that's what the question was asking us about. The point when we reach maximum compression. So the key thing that you realized here is that you needed a different framework for the 2 different intervals. For this first interval between these 2 instants, you used conservation of momentum. And how did you know to do that? Well, the key is conservation of momentum is usually used for collisions, and that's what's happening here, a collision. So we can use conservation of momentum. And then after the collision, the framework that you used was conservation of mechanical energy. Because at this point now we have an oscillating spring, and we've seen how to use conservation of mechanical energy for that. So one thing that you saw is that your initial and final points changed. During the first part of the problem, the initial point was t0 and the final point was t1. But then when you moved over here to conservation of mechanical energy, you shifted, and now the initial point was t1 and the final point, I guess I could call that t2, actually. So you did that correctly. So I'm just showing the way to think systematically about how you attack this. So we haven't worked on conservation of momentum here, but you remembered how to apply that. You used the key equation for conservation of momentum that we put on the board, and you worked that out. Good. So the main focus today is oscillations, but I wanted to go over this because this is one of the common ways that this concept is tested. Very often in exams, they like to combine the spring with the conservation of momentum from earlier. So this is pretty typical of a pretty typical type of exam problem. Okay, and you did that first part correctly, and then again you shifted over to conservation of momentum here. Okay, good. I'll just point out to you that one trick you can use in these problems is cancel the halves, and then the calculations turn out to be a little bit easier. Okay, but you didn't make any mistakes, and you got the correct answer here. So that's good. I think a lot of students would have trouble with that because you have to combine 2 different intervals and 2 different frameworks, but you did that correctly. Okay, and I could then ask you more questions. I could ask you, how long does it take to reach maximum compression? How would you figure out how long it would take to reach maximum compression?
Would we do what we did before with the spring constant and the mass?
You tell me, would that work?
Yeah.
Good. And then, so you would use that to figure out?
The period. And
then you would use the period to figure out?
It would be a quarter.
It would, again, be a quarter of a cycle. Okay, excellent, good. Okay, so this is an example of how you can write a question that combines the oscillations with the earlier stuff about collisions. And you used a good process for attacking that, that's good. Okay, all right, well I think you're understanding those key ideas there about the horizontal spring. So let's move on to another type of oscillation that's on the homework. So another type of oscillation on the homework is pendulums. So let's talk about how to deal with that. So let's say here's the ceiling, and here's a rope, and here's a mast that's attached to the pendulum. So the mast that's attached to the pendulum is called the bob. So we have a 2-kilogram bob here. We assume that the rope has 0 mass, and all the mass is at the bob at the end. So if I pulled the pendulum out to here and I let go of it, what would happen?
It would start swinging back the other way.
Yeah, it would go like this. And if there was no air resistance, it would keep doing that forever. If there was no air resistance, it would keep going back and forth forever. So you can see that looks like another type of oscillation, a lot like a spring. So we can use many of the same ideas in order to deal with that. So remember that the key points for the spring were maximum expansion, maximum compression, and the natural length. So what will be the key points for the pendulum? Well, the key points are maximum leftward swing, maximum rightward swing, and what else?
And the middle point? Or
The vertical.
The vertical, yeah.
So by the way, if the string is 10 meters long and we pull it 2 meters from the ceiling, what would this distance be?
8 meters?
Good, because what's this distance?
10.
10, because it's still the same string.
Yeah.
And this is 2, so that's a little geometry that you might have to do on a pendulum problem.
Okay.
Okay, good. Okay. So, what's the framework that we're likely going to use to analyze a pendulum?
Conservation of mechanical energy.
Conservation of mechanical energy again. That's right. But what types of energy are relevant to the pendulum?
Gravitational potential and kinetic.
So now we're not going to deal with the spring energy anymore. So what are the key things that we need to characterize this? The key variables now would be not v and x, but v and h. Now our key variables are v and h instead of v and x. So for example, what could you say about v at this point?
It's at 0.
How do you know?
Because it's at its max, because it's all potential. And that's...
How do we know v is 0 here?
Change direction.
It's changing direction. That's right. Although you could also use conservation of energy to figure that out. That's right. But we know we're changing direction. That's the most straightforward approach. Good. And what can you say about the h at this point?
Is at its max?
Yeah. So I meant these to be the maximums over here. So this would be the maximum h. Good. So what can we say about the kinetic energy here?
It is at 0.
Because v is 0. And what can we say about the gravitational energy?
It's at its max. It's all there.
There's 2 ways to see that. First of all, the height is maximized, so the gravitational energy is maximized. And also, if there's no energy in kinetic, it must all have gone into gravitational. Okay, good. So what can we say about this point?
The velocity is at its maximum.
And what else?
And so is the kinetic energy. And then there is no potential energy. Potential energy equals 0 and the height is equal to 0.
Now this is assuming that we decided to define this as 0 height. You can define anything you want to be 0 height, but it's certainly most convenient on these problems to define the vertical position as 0 height. So yeah, we're always going to define the vertical position as 0 height. So if we define the vertical position as 0 height, then there would be 0 gravitational energy here. So how did you know that the kinetic energy would be maximized here?
Because potential energy is 0.
From conservation of energy. If there's no energy here, it must all have gone into kinetic. So really, logically, we should have started with these ideas and moved over to here. But what you said was correct. And how did you know that V is maximized?
Because of kinetic energy.
So logically, that comes last. But everything you said was correct. Okay, good. So then what would we say about this point?
The same thing as the... You want me to go through it all?
Same thing as over here?
Yeah.
All right. So you can see we end up with a kind of a similar table that we did for the spring.
Yeah.
Okay, good. Now what about our little flow chart up here? Now, which parts of this apply and which don't? Well, will the pendulum still have a period?
Yes.
So that still applies. What does the period tell us?
How how many seconds it takes to complete a cycle.
So for example, if it starts here, it'll tell you how many seconds it'll take to get back to here.
Okay.
And will the pendulum have a frequency?
Yes.
And what does that tell us?
How many cycles it completes in 1 second.
So it will tell us in 1 second how many back and forths it does. And you can still have an angular frequency as well. For example, if the angular frequency was 6 pi radians per second, what would that tell you about the pendulum?
3 cycles. It completes 3 cycles in 1 second.
Good. But here's where we went into problems because a pendulum doesn't have a K. So this last part of the flow chart doesn't apply here anymore. So what was this useful for? This was useful for figuring out omega from the physical characteristics of the spring. So we're going to need a different way to figure out omega from the physical characteristics of a pendulum. So it turns out there's a different formula for a pendulum. So here's the formula for a pendulum. So what does this symbol stand for?
Acceleration of gravity.
Acceleration due to gravity. That's right. And what do you think this is?
The length of the rope string.
Yeah, the length of the pendulum. So what would L be in my example here?
10 meters.
Yeah. Before I was trying to warn you that X is not the length of the spring, but L really is the length of the pendulum. Okay? So we can say that we're tying this with L, the length of the pendulum. What would be the SI units for L?
Meters.
So if L was given in centimeters, we'd have to do a unit conversion before we could use this formula. Okay, all right, so here's the part of how we would adapt the flow chart if we were dealing with a pendulum. All right, good. This is the ones we did, maybe number 4?
Yeah, 4 I think.
Okay. Okay, let's give this a shot. Okay. Okay, good. So I think what you saw here is that, like the previous problem, there was 3 key points in time. So first of all, here, the initial point was the instant before the collision, and the final point was the instant after the collision. And used conservation of momentum for that. Good. And then, for the second part of the problem, the initial point was the instant after the collision, and the final point was when it reached the highest height. So you shifted your initial and your final points. So that was good. How did you know the initial gravitational energy was 0? Because it was at the vertical position. So you defined that as 0 height. How did you know the final kinetic energy was 0?
Because there was no flux, it was changing direction, so the velocity is 0.
Yeah, because it's changing direction at that point. That's one of the parts that gives people the most trouble here, realizing that this is 0, because it's changing direction. Because it didn't ask for when it's changing direction, it asked for how far up does it get.
Right.
But we need to realize the highest point it reaches is when it's changing direction. Okay, good. Something you can do to save time here is cancel the masses at this point in the problem. Okay, but I think you still did your calculations correctly. And then the second part, we had to move over to the flowchart. And we moved again from one end of the flowchart to the next. Students often get this wrong because they divide by 2. They think that they're going half of a cycle because it looks like you're moving halfway on the picture.
Right.
But as we talked about before, that's really a quarter of the cycle.
Okay.
Because a complete cycle would be going back and forth. So it looks like you got that correct too. Okay, very good. So that's the correct way. So again, if this part of oscillations is tested on an exam, it's often tested together with conservation of momentum in this type of problem. Okay, good. Okay, I think that really covers what you're likely to see on a test about pendulums, so make sure you got that down. So the other type of oscillation in the homework, what have we talked about so far? We talked about a horizontal spring, and we talked about a pendulum. And the only other type of oscillation in the homework was vertical springs. And those turn out to be a little bit different than horizontal. So let's look at that. So if you have a horizontal spring that is completely at rest and no one is touching it, what position will it take?
What do you mean?
So if you just leave a spring by itself,
It won't move.
yeah, and how long will it be?
It's natural length.
Its natural length, yes. So if you leave a spring by itself and you don't touch it, if it's horizontal, it'll assume its natural length.
Okay.
But if you think about it, that's not true for a vertical spring. A vertical spring, even if you're not touching it, it can't assume its natural length because then it couldn't balance the mass. Right? Notice that here, the spring doesn't have to balance the mass because the mass is on the floor. The floor is supporting the mass. But a vertical spring has to support the mass, so it has to exert a spring force. So you can kind of just use your common sense here. If there was no mass, the spring really would have its natural length. But what happens if you attach a mass? If you attach a mass, that'll tug the spring down a little bit. And then, it can just be motionless at this point. So the point is that the point that the spring will be at when you're not touching it is no longer the natural length. We could call this the equilibrium length. So this is now the equilibrium length. If you take a horizontal spring and you compress it away from, and you compress it, and then you let go, it will start oscillating. What point will it oscillate around?
Its natural length.
It'll oscillate around the natural length. The natural length will be halfway along the oscillation.
Okay.
If you take a vertical spring and you tug it down further and then you let it go, it will oscillate. But what point will the vertical spring oscillate around?
The equilibrium length.
Not the natural length.
Right.
That's right. So another name for this equilibrium length, we could also call this the midpoint of oscillation. A vertical spring doesn't oscillate around its natural length, it oscillates around a different midpoint, it oscillates around the equilibrium length. Okay, so that's one difference between a vertical and a horizontal spring. Now another difference is, what's the main framework that we've been using for analyzing springs?
Conservation of energy.
Conservation of mechanical energy.
Mechanical.
When we were dealing with pendulums, what types of energy did we focus on?
Gravitational and kinetic.
For pendulums. And for horizontal springs, what types of energy did we focus on?
Spring potential energy and kinetic.
We didn't need gravitational energy because the gravitational energy wasn't changing. But you notice now what types of energy are relevant.
All three of them.
All three, because now the gravitational energy will change. So at first it seems like these are going to be substantially more difficult problems because we're going to have three terms to take care of. But fortunately there's a trick that makes these just about as easy as the horizontal springs. We just need to learn the trick. So a naive student would think that they needed to use this term and this term. But fortunately the physicists came up with a trick. They figured out that for a vertical spring, you can combine these into a single formula. For a vertical spring, we can combine these into a single formula. For a vertical spring, the combined gravitational and spring energy is given by this formula. So notice I'm not calling it gravitational or spring, this is actually the combined gravitational and spring energy. So we're not going to prove that this is true, but this is just a useful trick that other people have proven is true. You might not have seen this in the book just because the book would probably still write this as 1/2 kx squared. But I think it makes more sense to use a y because y is usually our vertical axis.
Yeah.
And that way also we won't confuse it with this equation that we used for horizontal springs. Okay. So you might not see this exactly this way in the book. They'd write it as 1/2 kx squared, but it's pretty much the same thing. Okay. So what do you think? So what does this stand for?
Spring potential energy.
The combined spring and
Oh,
gravitational energy.
Yeah.
This is why we're not going to need to use this term,
Right.
even for a vertical spring. So here's the point. Even for a vertical spring, we still don't need this equation because it's actually included in this new formula.
Okay.
It's not obvious that it is, but if you did the math, you could see that it is.
Okay.
Okay. What's this stand for?
Spring constant.
And what do you think this stands for?
The displacement?
From what?
From the point, from equilibrium. Like.
Yeah. That's why these two formulas look very similar, but there's actually a significant difference. This is the displacement from the natural length,
Okay.
but this is the displacement from the equilibrium length, which we saw was not the same thing as the natural length for a vertical spring. The easiest way to think of this is the displacement from the midpoint of the oscillation.
Okay.
This is the displacement from the midpoint from the oscillation. So even though these formulas look very similar, there is a little bit of a difference between them. Okay, so it turns out that even though at first it might have seemed like vertical spring problems are harder, they're not really any more complicated as long as we know this shortcut formula that we can use. So what types of energy are we going to have to take into account for a vertical spring? What will be the formulas that we're using for energy for a vertical spring?
That one and kinetic.
So we'll need this formula,
Yeah.
and will we need this one?
No.
No, instead we'll use this one.
Yeah.
Okay, good. And what about our flowchart up here? Well, fortunately, the flowchart still works with no changes.
Okay.
So all of this stuff that we said here for springs works for both vertical and horizontal springs. Okay, so let's see. Oh, let's give this a shot.
That's not right. that's my answer.
Okay. One thing that makes this problem a little bit trickier than the ones before is I didn't really kind of tell you what the initial and the final points were here.
Yeah.
I didn't tell you where it was starting and ending. But as I think you kind of figured out, that doesn't really matter. All you, the 3 points that we ever really care about in these problems are maximum height, middle, and maximum depth, basically. You want to pick one of the points that you know something about and one point where you're trying to figure something out. So when they were asking you for the maximum speed, you figured out the maximum speed would occur at the midpoint. So you picked that as one of the points. And then the point that we know, another point we know a bunch about is maximum height or maximum depth. So you picked that. I think it might have been a little more natural to say this was the initial point and this was the final. But
Yeah,
it doesn't mess up your answer at all. You dealt with that just fine. So if you said this was the initial point here, so the key thing here is it asked you for the maximum speed. You figured out the maximum speed would occur at the midpoint.
Yeah.
How do you know the maximum speed will occur at the midpoint?
Well, I wasn't, I knew that there was no kinetic energy here.
How do you know that's
Because
zero?
it's about to change direction.
So the V is zero.
Yeah,
That's
so
right.
I knew that's when this would be whatever it is. But I got like kind of confused for a second. So would this really, that would be zero because we would set this height to zero? Because what was
So remember, the
throwing me
thing
off
we're
is
focusing on is Y.
Right.
So, and this is the midpoint, right?
Okay,
So what
so
is
show me.
Y at the midpoint?
Zero.
Because what's Y defined as? Y is defined as displacement from the midpoint.
Right.
So remember that Y has a little different meaning from X in
Yeah.
our previous formula. Y is defined as the displacement from the midpoint. So it's not exactly the height. It's the displacement from the midpoint.
Yeah,
so at the midpoint, Y is zero. So what is the U at the midpoint?
Zero.
Because Y is zero.
Yes.
Good. And therefore, what do you know about the kinetic energy at the midpoint?
It's at its max.
Because none of the energy is potential.
Yeah.
So what do you know about the speed?
It's at its max.
All right, and this is all stuff that you were figuring out kind of on your own. All right, so you figured out that when they asked you for the maximum speed, they meant the speed at the midpoint. All right, and you must have been thinking of some kind of logic like this. Okay, that's correct. So that's why you were able to plug in zero kinetic. You were saying at this point, all the energy would be kinetic. There's no potential energy. And then you focused on this point because we knew something about it. So you said there's zero kinetic energy here because the speed is zero, 1/2 ky squared. One thing you did was good is the distance I gave you was 0.5 meters. But you figured out that the distance to plug in here was 0.25 meters. So that's good because 0.5 meters is from one end to the other. But the displacement from the midpoint was half that. So
Right.
you showed that in your picture. That's good. And then you worked out the answer. Okay, so yeah, we didn't go through all the details ahead of time, but you still worked this out. That's good. So what would be the amplitude of this oscillation?
The amplitude would be 0.25 meters.
Good, that's right. We haven't been practicing amplitude much,
Okay.
but a lot of students might think the amplitude was 0.5, but as you
Right,
said
yeah, I
correctly,
almost
it's
said that,
0.25.
yeah.
Okay. All right, so that's the correct amplitude here. How could we figure out how long it would take to go from maximum height to minimum height? Let's just verbally work out. How would you figure out how long it would take to go from maximum to minimum height?
You could get the angular frequency with the spring constant and the mass.
Yeah, so you could use the omega equals root k over m, and then use the flow chart to figure out.
The period,
Okay.
and then you would divide by 4.
So the question was, how long does it take to go from maximum height
Oh,
to
sorry.
minimum height?
Divide by 2.
Because that would be half a cycle. That's right, so you'd have to pay close attention to what the question was asking you to work that out. Okay, so as it turned out, even though theoretically vertical springs are more complicated than horizontal springs, because the physicists have come up with a shortcut, the problems are not really any harder for us.
Right, okay.
You might think that you'd have, so the key thing is we don't need the MGH term. We don't need the MGH because even though it's not obvious, it's really packed inside of this equation right here. So that's the key thing to keep in mind. Even though gravitational energy matters here, we're already taking into account with the 1/2 ky squared formula. So that it turns out the problem is really no more difficult than the horizontal springs once we know that trick. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you.